You've got a room full of people at a party and something strange is going on. Some of these people absolutely love each other and they keep trying to get closer and closer. Others can't stand each other and they keep pushing away, trying to get to opposite corners of the room. Now the funny thing is, you can't tell by looking at them which ones will attract and which ones will repel. There's just something about them, some invisible property that makes them either love or hate each other on sight. That's exactly what's going on inside all matter. Inside atoms, there are these things called protons and electrons, and they have this property we call charge. The protons are positive and the electrons are negative. And a positive and a negative, they love each other, they attract. Two positives or two negatives, they hate each other, they repel. Nobody really knows what charge is in a deep sense. We know what it does, but why it exists, that's one of those secrets nature keeps to herself. Now think about a big dance party. You've got groups of people standing around, and most people stay with their group. But some people are wandering around free, going from group to group, dancing with whoever, saying hello to everybody, not tied down to any one spot. Now imagine a different party where everybody is tied to their chair. They can see each other, they might want to move around, but they can't go anywhere because they're stuck. That's the difference between a copper wire and a piece of rubber. In copper, the atoms are like those groups at the party, and some of the electrons are the wandering people. They can drift from atom to atom through the whole wire. We call them free electrons, and that's what makes copper a conductor. In rubber, the electrons are tied to their chairs. They're stuck to their atoms, and no matter how much they want to move, they can't. That's an insulator. Prisoners. So when you wrap a copper wire in rubber, what you've got is a party of free wandering people on the inside, surrounded by prisoners on the outside who keep everything contained. The electricity can flow through the copper, but it can't escape through the rubber. That's the whole trick of electrical wiring. Now think about a cup of hot coffee sitting on a table. It's hot, right? And after a while, the cup gets warm and the coffee gets cooler. What's happening in there? The atoms in the hot coffee are jiggling like crazy, bouncing around, bumping into each other. And when they hit the atoms in the cup, they make those atoms start jiggling too. It's like a ball bouncing on the floor, you see. The ball hits the floor and makes the floor atoms jiggle a little faster. Each bounce, the ball loses some energy and the floor gains some. That's what heat is. It's jiggling. Hot means jiggling fast. Cold means jiggling slow. When hot things touch cold things, the fast jigglers bump into the slow jigglers and get them moving faster. The heat spreads. Now, when electricity flows through a wire, something similar happens. Electrons are drifting along, and they're bumping into atoms as they go. Every bump makes the atoms jiggle a little more. That's why wires get warm when current flows through them. All those little collisions are speeding up the jiggling. The electricity is literally shaking the atoms as it passes by. Now, when I was a kid, I had a bicycle, and I noticed something funny. When you pump up the tire, the pump gets hot. I wondered about that, you see. What's happening is, you push the handle down, and the air molecules get squeezed together. They bump into each other more and more, and they start jiggling faster. More jiggling means hotter. But here's the other thing. When you push at the top of the pump, the effect reaches the bottom almost right away. The pump is already full of molecules packed together. So when you push at the top, the molecules bump the ones below them, who bump the ones below them, and the push travels through very fast, even though each individual molecule barely moves at all. Same thing in a wire. The wire is already packed full of free electrons. They're all just sitting there waiting. When you push some in at one end, they bump the ones in front of them, who bump the ones in front of them, and the effect shoots through at nearly the speed of light. Each electron is crawling along very slow, but the push is flying. Now, for electricity to actually do anything useful, you need a complete loop. If those free electrons in the copper wire are going to drift along, they need somewhere to go and somewhere to come from. If there's a gap anywhere in the path, they just pile up at the edge and stop. Nothing moves. When you flip a light switch, what you're really doing is completing a loop. The electricity flows from the power source, through the wire, through the light bulb, and back to the power source. The moment you flip that switch off, you've broken the loop, and everything stops. That's what a circuit is, a complete path for the electrons to travel around. No complete path, no electricity. Simple as that. Now here's something that should really bother you. This electric force between charges is not just a little stronger than gravity, it's about 10 to the 42 times stronger. That's a 1 with 42 zeros after it. The number is so absurd, it doesn't mean anything. So let me put it a different way. You're standing next to another person. Inside both of your bodies, there are enormous amounts of protons and electrons pushing and pulling on each other with this tremendous force. And you feel nothing. Zero. Why? Because the positive and negative charges in your body are almost exactly equal in number. They cancel out. The attractions and repulsions balance so precisely that what's left over is just this tiny residue we call gravity. You know, the thing that keeps your feet on the ground? That's the leftover. That's what sneaks through after the electrical forces have canceled themselves out. Now here's the disturbing part. If you and that person next to you each had just 1% more electrons than protons, not double, not 10 times more, just 1% out of balance, the repulsion between you two would be strong enough to lift the entire Earth, the whole planet. That's how strong this force really is. And we never notice because nature keeps the balance so incredibly precise. This is why the ancient Greeks only knew 2 electrical phenomena in the whole world. They found that if you rub amber, it picks up bits of straw. And there was a strange stone from magnesia that attracted iron. That's it. 2 little curiosities out of everything. They had no idea they were playing with the force that holds all matter together. The balance was just too perfect for them to see what was really going on underneath. And this balance explains something else, too. All of chemistry, every reaction that ever happened, is electrical. When atoms come together to form molecules, it's the electrons rearranging themselves. When wood burns, that's electrons finding new partners. When you digest food, same thing. The nuclear forces are locked up tight inside the nucleus and don't care about chemistry at all. Chemistry is entirely a story about electrons and the electrical forces between them. Life itself is an electrical phenomenon, and we walk around thinking electricity is just that thing that comes out of the wall.
Now we've got electrons that can move through a wire. But what makes them actually move? They need a push, you see. Something has to get them going. Think about water in a pipe. If the pipe is perfectly level, the water just sits there. But if you raise one end higher than the other, the water flows downhill. The bigger the height difference, the harder the water pushes through. That height difference is like what we call voltage in electricity. It's the pressure that pushes the electrons along. A battery or a power plant creates this pressure. It piles up electrons on one side and takes them away from the other side. And that imbalance is what drives them through the wire when you complete the circuit. Now here's an interesting thing. Not all wires let electricity through the same way. A thin wire is harder for electricity to get through than a thick wire. It's like trying to push water through a skinny straw versus a fat pipe. The skinny straw fights back more. We call this resistance. Everything has some resistance, and it determines how much current you get for a given voltage. And here's what happens with that resistance. Remember the electrons bumping into atoms as they drift through? Every bump transfers a little energy and makes the atoms jiggle more. More resistance means more bumping, which means more jiggling, which means more heat. That's why a light bulb glows, you see. The filament inside has high resistance, so when electricity pushes through, all those collisions make it so hot it produces light. The bulb is basically a piece of wire that's bad at conducting on purpose. This is also why short circuits are dangerous. If electricity finds a path with very low resistance, it rushes through like water bursting through a broken dam. All that current flowing through the wires makes them heat up fast, and if there's too much current, the wires can get hot enough to start a fire. That's what fuses and circuit breakers are for. They break the circuit if too much current tries to flow through. Now what about when you get a shock? What's happening there is electricity is flowing through your body. Your body is actually a decent conductor because it's mostly salty water, and salt water conducts pretty well. When you touch something with high voltage and you're also connected to the ground, the electricity sees a path. It can go through you into the ground, and it takes that path. The current flowing through your muscles makes them contract, and that's the jolt you feel. Enough current and it can stop your heart. That's why electricians are so careful about grounding and insulation. So you've got voltage pushing the electrons along and resistance fighting back. and the balance between them determines how much current flows. That's really the whole game of practical electricity. Now here's where it gets really interesting. Electricity and magnetism, they seem like completely different things, right? One is about charges flowing through wires, and the other is about those strange forces that make compass needles point north and let magnets stick to your refrigerator. But they're not different at all. They're the same thing. When electricity flows through a wire, something happens in the space around that wire. A magnetic field appears. You can test this yourself. Put a compass near a wire carrying current, and the needle moves. The electricity creates magnetism just by flowing. Wrap that wire into a coil, and the magnetic field gets stronger. Wrap it around a piece of iron, and you've got an electromagnet. A magnet you can turn on and off just by controlling the current. Now here's the beautiful part. It works the other way too. If you take a magnet and move it near a wire, you create electricity in that wire. No battery needed, just movement and magnetism. And suddenly, electrons start flowing. This is how generators work, you see. At a power plant, they spin big magnets inside coils of wire, and that motion creates the electricity that travels to your house. The energy of the spinning gets converted into electrical energy. Think about that for a moment. A river pushes a turbine, and the turbine spins magnets, and the spinning magnets push electrons through wires, and those electrons travel hundreds of miles and push the electrons in your lamp and make the atoms jiggle until they glow. The water never touches the lamp, but the energy gets there. It's really quite wonderful when you think about it. Motors are the same thing, running backwards. You put current through a coil near a magnet, and instead of the motion creating electricity, the electricity creates motion. The coil wants to spin. That's how every electric motor works, from the fan on your desk to the big machines in factories. Current plus magnetism equals motion. Motion plus magnetism equals current. Two sides of the same coin. Now, a fellow named Maxwell figured all this out and wrote it down in a few equations. And when he looked carefully at those equations, he found something nobody expected. The equation said that when you jiggle a charge back and forth, the electrical and magnetic disturbance travels outward through space. And they said exactly how fast it travels. When Maxwell calculated the speed, it came out to be the speed of light. Exactly the speed of light. That was no coincidence. Light is electricity and magnetism traveling through space together. When you see a candle flame, or watch a sunset, or read these words, what's hitting your eyes is electromagnetic waves. Electricity and magnetism jiggling together, moving through space at tremendous speed. Radio waves are the same thing, just jiggling slower. X-rays are the same thing, jiggling faster. It's all the same phenomenon. Now let me tell you something that's going to change how you think about the world. You've been touching things your whole life, picking up cups, shaking hands, pushing doors, but you've never actually touched anything. Not once. When your hand pushes against a table, what's really happening is the electrons in your skin are getting close to the electrons in the table, and they're both negative, so they repel. The atoms in your hand never actually meet the atoms in the table. They get close enough to feel that electrical repulsion pushing back, and that's what you call touch. It's like trying to push two magnets together when they're facing the wrong way. They fight back before they ever meet. Your whole life, every single thing you thought you touched, you were really just feeling electrical forces across a tiny gap of empty space. This is why matter feels solid, you see. The floor holds you up, not because atoms are hard little balls that stack on top of each other. The floor holds you up because when you push down, the electrons in your shoes repel the electrons in the floor. It's an electrical argument happening at every point of contact, and the argument is so fast and so strong that it feels perfectly solid. Now here's another one. When people talk about nuclear energy and atomic bombs, they use the word nuclear because the energy comes from the nucleus breaking apart. But what kind of energy is actually released? Think about what's happening in there. The nucleus has protons in it, and they're all positive. They should repel each other and fly apart. But there's this other force called the nuclear force that holds them together. It's stronger than the electrical repulsion, but it only works at very short distances. So the protons are stuck there, wanting to fly apart electrically, but held in place by the nuclear force. Uranium has 92 protons crammed in there, and that's a lot. The nucleus is barely holding together. Now you send in a slow neutron, and the whole thing splits in two. And when it splits, you've got two chunks, both positively charged, and they fly apart from each other. What's pushing them apart? Electrical repulsion. Same force that keeps your hand from touching the table. So the energy of an atomic bomb, the tremendous explosion, is electrical energy. The nuclear force was just the lid holding it in. When the lid breaks, the electrical force finally gets to push those pieces apart at tremendous speed. People call it nuclear energy, but really it's electrical energy that was locked up and finally got released. Everything comes back to this one force, the charge, the push and pull of positive and negative. It holds atoms together and blows nuclei apart. It makes matter solid and makes lightning strike. It's everywhere doing everything, and we barely notice because it's so perfectly balanced in everyday life. You see birds sitting on power lines all the time, and they're perfectly fine. Why don't they get electrocuted? Remember, electricity needs a complete path to flow. The bird is sitting on one wire with both feet. For electricity to go through the bird, it would need to enter one foot and leave through the other. But both feet are on the same wire at almost the same spot. There's no difference in electrical pressure between the 2 feet, so no current flows through the bird. The electricity just keeps going through the wire because that's the easier path. Now, if that bird was big enough to touch 2 wires at once, or touched a wire and a pole at the same time, different story. That's why power company workers are so careful about what they touch and when. Same reason water and electricity are dangerous together. Your body by itself has some resistance, but when you're wet or standing in water, that resistance drops because water with a little salt in it conducts very well. Now you become an easy path for electricity to flow through you into the ground. A hairdryer falling into a bathtub, the electricity suddenly has a beautiful path right through the water and right through you. This is why we have this thing called grounding. The ground itself is a huge conductor, you see. We connect part of the electrical system to the earth with metal rods. If something goes wrong and electricity escapes from where it should be, it takes the easy path into the ground instead of through you. The earth just absorbs it like a giant sponge. And lightning, that's nature's version of this. Clouds build up enormous amounts of charge. The bottom of the cloud becomes very negative, and it's looking at the ground, which is positive by comparison. The electrical pressure builds and builds until the air itself breaks down and becomes a conductor for a split second. Then, boom! All that charge rushes down to the ground. Lightning strikes tall things because the taller something is, the closer it gets to the cloud and the easier it is for the spark to jump. Now, a fellow named Faraday figured out something in 1840 that changed the world. He discovered that when you move a magnet near a wire, you create electricity. Before that discovery, there was no way to make electricity flow continuously. You had batteries which ran out, and static electricity from rubbing things. Faraday showed you could make it forever just by spinning. And that discovery, you see, that's why you have lights in your house. Somewhere far away, water is falling, or steam is pushing, or wind is blowing, and that motion spins magnets inside coils of wire, and electricity flows out through hundreds of miles of wire to wherever you need it. The motion of a distant river becomes the light you read by at night. Faraday made that possible, and we're still using his discovery every single day. Now, after all this, you might think we understand electricity completely. We've got equations that predict exactly what will happen. We can build machines that use it. We can send it across hundreds of miles. But here's the funny thing. We don't really know what it is. What is charge? I mean, really, what is it? We know what it does. We know positive repels positive and attracts negative. We can calculate the forces and build motors and make light bulbs glow. But why does charge exist at all? Why these rules and not some other rules? Nobody knows. We've just discovered that nature works this way, and we've learned to describe it. And that's the honest truth about physics, you see. We're not really explaining anything in a deep sense. We're discovering patterns. We notice that when we do this, then that happens. We write it down. We find that the same pattern works in many different situations, and we give it a name, like electricity, or magnetism, or charge. But the name isn't an explanation. It's just a label for something we've observed. The Greeks rubbed amber and picked up bits of straw and thought it was a curiosity. They had no idea that the same force holds atoms together and makes lightning strike and powers every living cell. We've come a long way since then. We know now that almost everything we see and touch is electrical, but we still can't answer a child who asks why charges attract and repel. We just say, that's how nature is. And I think that's wonderful, actually. Nature's imagination is so much greater than ours. Every time we think we've figured it all out, she shows us something new, something we never expected. The universe is not obligated to make sense to us, and yet somehow we can understand pieces of it. We can predict what will happen and build things that work. That's remarkable when you think about it. So electricity, this invisible force that's been there all along, holding matter together and making chemistry work and carrying energy across the world. It's one of those patterns we've learned to see. We know how to use it. We can do the arithmetic and make it work for us. But the deep question of what it really is, that's still open. And I find that exciting, not frustrating. It means there's more to discover. There's always more to discover.